Okay, let's talk about your inhibitors. Now, there are two types of inhibitors. You have your reversible and your irreversible. Now, the irreversible we're not going to really talk about, but what does an irreversible inhibitor do?
Creates a covalent bond.
So often creates a covalent bond and irreversibly binds to your enzyme, inactivating it completely forever. Done. Enzyme's done. Sweet, we're not going to talk about those. They're very easy kinetics. Over. So we're going to talk about a little bit more difficult situation, but it's still not bad. And we'll talk about the two types of reversible inhibitors. Now, truth be told, there's actually not just two types of reversible inhibitors. We're only going to talk about two types in this class. So, and the first type we're going to talk about is competitive inhibition. Competitive inhibition. So if we go back and look again at our general mechanism here, E plus S goes to enzyme substrate complex, which then can produce product. In fact, I think I might just make a little more white space here. So in this case, competitive inhibitor. You guys have already had this. I get the honor of getting second exposure here. What's a competitive inhibitor? So active site, good. Competes for the same binding site as the substrate. So it's trying to bind to the exact same spot as your substrate. So in this case, we're going to do an enzymatic reaction. And we're going to call this enzymatic reaction Chad eats a lollipop. That's what it's going to be. And so here's the way me eating a lollipop works. First thing that's got to happen, that lollipop's got to get to my lips. And it binds to my lips, and I'm like, oh, that's good. So, and then the lollipop slips in my mouth, and I eat it. Cool, that's it. So notice we have substrate binding, and that's what happens at the lips. And then I chomp down and swallow, and that would be the catalysis part, analogous to that anyways. So if we look, what could compete with, Chad eating a lollipop? Well, if I had a bunch of lollipops sitting out here, I'd be like, sweet, and I'd just eat one after the other. And I'd be saturated, and I would go at max velocity until there wasn't so many lollipops around, right? So, but how do I compete with that? Well, we just put a bunch of popsicles around. I'm like, oh, lollipops and popsicles. Holy cow, what do I do? And so lollipops can bind to my lips, but so can popsicles. And the more popsicles you put, the less lollipops I see, and so on and so forth. Now, they're binding for the same active site. That's why they're analogous to being a competitive inhibitor in this case. How could I overcome that, though?
Putting in more substrate.
Yeah, putting in more lollipops, in this case, more substrate. And so in this case, if you put 10 popsicles and 10 lollipops, I see lots of both. But if all of a sudden you fill this entire room, floor to ceiling, with 1 million lollipops, and there's still just 10 popsicles, one, I'm going to have a hard time finding a popsicle, and I get back to being the same Vmax as if the popsicles weren't even there, as if the inhibitors weren't even there. And so for your competitive inhibitors, we see the way it works is that they can bind the free enzyme, forming an enzyme inhibitor complex. And when the inhibitor's bound, you can't bind substrate. When the substrate's bound, you can't bind inhibitor. So, but the idea is if you throw in even more substrate than normal, you can overcome this. Then you have enough substrate to outcompete the inhibitor, and you get to the same Vmax. And so that's why in competitive inhibition, you have the same Vmax. So, but it turns out it's going to change the Km value. It's going to change the Km value. Now that there's something competing for the active site, it changes the binding, if you will, with my substrate in some way, shape, or form. In this case, is it going to make the Km higher or lower?
Higher Km.
Higher Km, because a higher Km means lower affinity for substrate. Cool. That's what a competitive inhibitor does. It doesn't change Vmax, but it increases the Km. Sweet. So let's look at this for a minute. Now I need to know, now that I know what it does, I need to interpret that graphically. What does that actually mean on the graph? Well, in this case, it doesn't change Vmax, so what's not going to change? My graph's still going to have to end up here somewhere. But what is going to change? Km. And so the point at which I reach halfway up here has got to change. So in this case, with inhibitor, this graph, with competitive inhibitor anyways, this graph might actually look like.
So Chad, your Km point is going to be at the bottom of that dotted line. It's not going to be at the intersection of the V and the Km part.
correct. No, Km has units of concentration, and so it's that point right there on the x-axis. So in this case with inhibitor, though, notice eventually, and I probably should flatten that out a little better, but eventually I'm going to reach the same, I'm approaching the same asymptote, the same Vmax. Vmax hasn't changed. But notice, to get halfway there, now all of a sudden, my new Km value with the inhibitor present is much, much higher than the uninhibited reaction. Cool? Sweet. How's it going to affect my Lineweaver-Burke plot, my double reciprocal plot? Well, if we look here, should it affect the y-intercept? Not in this case. My y-intercept is just related to Vmax, and if Vmax doesn't change, then it doesn't change my y-intercept. So my next graph is still going to go through there. Should it change the slope, though? Yes, because slope depends on Km. Should it change the x-intercept? Yes, because x-intercept depends on Km. So let's look at this for a minute. The slope, Vmax doesn't change. Keep that in mind. Did Km go up or down with inhibitor? It went up, so my slope went up, which means now I'm going to have a steeper slope with inhibitor present. And so now I'm going to get something maybe like that. And the more inhibitor I put in there, the steeper that slope would get. So if I put in varying concentration of inhibitor, this slope would get steeper and steeper and steeper because Km would get higher and higher and higher. Notice it's still got to cross my y-intercept at exactly the same point because Vmax hasn't changed. But if you extrapolate this down, you'll see that the x-intercept is now at a totally different point. Again, and that's a reflection of the fact that Km is now a different number. Cool, you may get a graph like this, and you got one. If you look at this and you see that the y-intercepts are the same, but the slopes are different, you should be like, oh, I know what kind of inhibition that is. It's competitive. But you should also know which of these shows the inhibited and uninhibited graphs. Uninhibited is the lower slope. Inhibited with a higher Km is the steeper slope. Cool? All right, so now I want to talk about non-competitive inhibition. Now it turns out non-competitive inhibition is really just a special case of what we call mixed inhibition. Did she mention mixed inhibition at all? Good, then I'm not going to talk about it. Mixed inhibition would actually change both Km and Vmax, and we're never going to consider those cases. Now, non-competitive is a special type of mixed. And in non-competitive inhibition, it pretty much is going to do the exact opposite, at least the same exact opposite result as what competitive did. So competitive left Vmax alone, but changed Km. Non-competitive is going to change Vmax, but leave Km alone. So it's going to leave Km alone. Binding really hasn't changed, but Vmax is now going to be slower with an inhibitor present. Kind of makes intuitive sense. So we look at kind of how this works. Here's one example of how this might play out. Let's go back to our lollipops. So back to our lollipops. Lots of lollipops around. They approach my lips, they bind to my lips, and then I eat them. So I inhale them and chew them and whatever. So, but the binding happens at the lips. So, and once they're bound, then they can be eaten. Now, instead of putting a popsicle around me, instead you come up and you stab me in the leg with a knife. Now, is that the active site? No. But I'm not going to feel good about getting stabbed with a knife in the leg. And I'm going to be like, oh my gosh, oh, stab me in the leg, what'd you do that for? But because I'm in so much pain, what am I doing with my teeth?
Not eating lollipops.
They're clenched. And I can get a lollipop to my lips, but I can't eat it. Sweet. So binding can still happen. But processing the enzyme is not so easy to do, right? So binding hasn't been affected. Km is exactly the same. but Vmax is now much slower. Now notice, stabbing me in the leg caused a conformational change in the active site. Change the active site so that I now can't process substrate, right? So, and that's the idea. It's an allosteric effect, if you will, sort of, this inhibitor, because it's not affecting the active site. We'll talk about allosteric enzymes a little bit differently, because this is still a Michaelis-Menten. So, but this is an inhibitor that is affecting some other site than the active site. It causes a change in the active site, but it's binding somewhere else. All right, if we look at kind of how this works, a little more complex picture. Still have our standard Michaelis-Menten. From here, though, we could have enzyme interacting with inhibitor. Enzyme interacting with inhibitor. So, and once you bind inhibitor, so you can I still bind to substrate at that point? With a knife in my leg, can I bring a lollipop to my lips?
Yeah, but you can.
Sure. I can't do anything with it, but I can bring it to my lips and bind it. Sweet. So in this case, I could then interact this with substrate and have an enzyme substrate inhibitor complex. Now, this guy, if I lost the inhibitor, could then go back, and actually I should probably put that on the other side. If I go this way, I can lose the inhibitor. If I go this way, the enzyme substrate complex itself could go and bind the inhibitor. So notice the inhibitor could bind to that other site without or with the substrate bound. Why is that so?
Because substrate can still bind, it just can't produce product.
Yeah, substrate's binding at the active site. He's binding somewhere else. So substrate can still bind here because this inhibitor's binding somewhere else. They're not competing for the same site in this case. Cool. So let's see how this affects things graphically now. So again, here we have the plot with no inhibitor. How's this going to change now with a non-competitive inhibitor present? It's going to lower the Vmax. We're not going to make it out to here. We're going to make it out to somewhere lower. But what's not going to change? Km, the point at which we reach half of our new Vmax is still got to be this point right here. So if we look, instead of ending up out here, maybe I only end up, out here. But the place where I end up halfway to this point, still got to line up right there. And so that's what my graph might look like now. So here, I now have a brand new Vmax that I'm approaching asymptotically. But my Km value is still exactly the same as it was before I added this non-competitive inhibitor. Nothing different.
You have to distinguish, I don't know, I was just wondering if you should say like Emax inhibitor or something on that line.
In this case, I'm going to say inhibitor, but what kind of inhibitor are we specifically talking about right now? Non-competitive. So this is non-competitive inhibitor. Cool. So now if we look at our Lineweaver-Burke plot, and again, if we look at no inhibitor, and again, keeping in mind that our y-intercept is 1 over Vmax, and our slope equals Km over Vmax. And again, if we extrapolate back, our x-intercept is -1 over Km. Will my y-intercept change now? Yep. Y-intercept depends on Vmax. If Vmax changes, sweet, y-intercept's changing. Will my slope change? Yeah, it also depends on Vmax. So if Vmax changing, my slope's going to change. Will my x-intercept change? No. Since x-intercept only depends on Km, and with a non-competitive inhibitor, we have the same Km, and so it's my x-intercept that now is not going to change. So let's look at this for a minute. What happened to my Vmax? It decreased. If Vmax goes down, then what happens to 1 over Vmax? It goes up. So now we're not crossing the y-intercept, the y-axis there. We might be crossing it there. And I still got to go through this point, though. So if we extrapolate that back, so now notice my slope is steeper, because with a smaller Vmax, it's in the denominator of my slope. Smaller Vmax would mean larger slope, so it's steeper. Still goes through the same x-intercept, but different y-intercept. And again, this is your non-competitive inhibitor. Oh, one quick thing, by the way. When I added an inhibitor, this graph, did it get left shifted or right shifted? Right shifted. Sweet. Just want to make sure you realize that that's what we mean by right shifted, where the inhibitor graph is always to the right of the no inhibitor graph.
That's just on Michaelis Menten.
So that's on Michaelis Menten. We'll see what happens with our allosteric enzymes here in a sec as well.